Hi, my name is Manish Mehta, and welcome to my presentation for my final year project about the Techno-Economic analysis of the bus tire open scheme. Before I start my presentation, I'd like to thank my supervisor at university, Dr. Karmakar, and I'd like to thank my supervisor at United Energy, Dr. Hedi Dalvand. I'd also like to thank Mr. Adil Mahmood for his constant help and guidance throughout the project. Thank you.
Before we can understand how the bus tire open scheme works, it's important to know what a voltage sag is. So as we can see in this diagram, a voltage sag is a dip in voltage. So every voltage sag has a duration and a depth. Voltage sags occur due to a fault on a network. There's been a lot of study done by the University of Wollongong and by the power quality team at United Energy to look at the impact of voltage sag on customer equipment. From the study, it's been found that voltage sags cause industrial equipment in particular to malfunction. So this is equipment such as PLCs, adjustable speed drives, and process controllers. So these equipment are very sensitive to voltage sags, and therefore a lot of the industrial sites have their own switchgear and circuit breakers which trip when they notice this voltage sag. So when their circuit breakers trip, this causes downtime and loss of production, which can be very costly, and therefore we want to look to avoid the reflected faults. So now, if we look at the network diagram of a zone substation, we can see the transformers. We can see this symbol which represents everything upstream. We can see the two buses of a zone substation, and we can see the feeders of the buses at the zone substation too. So what happens is, when a fault occurs, there is a voltage sag. So this is without the bus tie open scheme. So without the bus tie open scheme, this bus tie circuit breaker is closed. And what happens is that when the fault occurs on this feeder, it propagates to all other feeders on this bus and also all the other feeders on the other bus. And that is why this fault is called a reflected fault, because it is reflected onto the other feeders and the other buses of the zone substation. So now that we understand what voltage sags and reflected faults are, it should make sense that we want to stop this original fault from propagating onto the other bus of the zone substation. And that is essentially the purpose of the bus tie open scheme. It is fast circuit breaker switching to isolate the fault onto one faulty bus and to allow the other bus or buses to be healthy and not see this voltage sag. So how this happens is that when the fault occurs on the faulty bus, the bus tie circuit breaker opens instantaneously, and therefore the fault is not reflected onto the healthy bus. And this provides enormous benefits for customers, because as we talked about earlier, voltage sags can have severe impacts on customer equipment, especially industrial customer equipment. It can lead to downtime and production loss. So now that we have a general understanding of how the bus tie open scheme works, hopefully the goals of my project should make more sense. So before I explain the goals, I just want to clarify that it hasn't been my goal to design the bus tie open scheme. The bus tie open scheme already has been implemented at a few zone substations at United Energy, and work has been done by the power quality team to look at the impacts of the bus tie open scheme on customers. So the primary goal of my project is to look at the impact of the bus tie open scheme on the company, so on UE, so on their assets, and also in terms of a cost analysis of the scheme as well. So to do this, I have used the power quality modeling software Siemens PSS Syncal. Another main goal of my project is to look at the settings for the bus tie open scheme. So in particular, this is the pickup delay and the minimum operational fault current level. That is a setting for the circuit breakers in the bus tie open scheme. So it's been my goal to define optimal settings for these values. So as I just mentioned, a primary goal of my project is to define the pickup delay settings for the bus tie open scheme. So you may ask, what is a pickup delay? Well, the pickup delay is the time in between the fault occurring and this bus tie circuit breaker tripping. So essentially we want as minimum pickup delay as we can get, because the greater the pickup delay is, the more time that the healthy bus is exposed to the fault. So at the moment, the pickup delays for various zone substations at United Energy are in this table here. So they are around 0.04 seconds and 0.1 seconds. I wasn't sure why this was the case, so I had to ask the secondary team at United Energy about what was going on, and they told me that these settings were in place to avoid a particular type of fault occurring, and I will explain this type of fault now. So when I went to the secondary team, they told me that this type of issue was occurring on poles which shared both 22 or 11 kV lines and sub-transmission or 66 kV lines. So for example, if we look at this image from Google Maps of a pole, we can see that there are the 66 or sub-T cross arms and then 22 or 11 kV cross arms. In order to best explain this issue, it's good to look at the diagram of a zone substation. So in this diagram we can see that it is a 2 transformer zone substation, and it has 2 buses, and also we can see that there are the circuit breakers in this diagram, which are represented by the squares. We can also see that over here we have the pole which shares both the feeder and the sub-T or 66 kV line. So at time equals 0 we can see that the fault has occurred on the feeder. Then after a small amount of time, the bus tie circuit breaker trips, so that's circuit breaker A in this diagram. And then after a small period of time, the feeder circuit breaker trips, which is circuit breaker E in this diagram. So the red line represents all customers which are out of supply. So what happens next is very interesting. So as we can see in this diagram, a secondary fault has occurred on the sub-T line, so on the same pole which is sharing both the 22 and the 66 kV lines. So this fault occurs due to an ionized ball of gas rising from the 22 or 11 kV line onto the 66 or sub-T line. So it's a rare type of fault, but it has happened in the past. And looking at past incidences, we can see that this time in between the first and the secondary fault occurring is around about 0.5 seconds. So when the secondary fault occurs, circuit breakers B, C, and D all trip, and this is a big issue because it means that there is no path for bus number 2 to be energized. So it's not just feeder E which is out of supply, now the whole bus is out of supply. So this is a considerable issue because it means that there are MAFI costs for United Energy because they are not meeting the regulatory requirements. So this type of issue does not just last for a few seconds, it lasts until circuit breaker A, which is the bus tie circuit breaker, recloses, which is not for 14 seconds. In order to stop this issue from occurring, there were a few options which were considered. The first option was to increase the pickup delay of the bus tie circuit breaker to more than 0.5 seconds, which was the amount of time it took for the secondary fault to occur. This option is not considered because if we increase the pickup delay to 0.5 seconds, for example, this would make the bus tie open scheme very inefficient, and it would render it pretty much useless. So we did not go with this option. Another option we considered was to rebuild both the distribution and the sub-T lines on separate poles, but this is extremely costly, so it's not an option that we considered. The more practical solution which we proposed was for a change of logic in the relays. So the change of logic that we want is for the bus tie circuit breaker or circuit breaker A to reclose whenever circuit breaker C or the transformer circuit breaker trips. So if this happens in this situation, we can see that bus number 2 is now energized from the other transformer and there is no outage on the bus. If this proposed solution is put in place, we can set the pickup delay for bus tie open scheme at all zone substations to be 0 seconds, which is the optimal value. Another goal of my project is to define min-op fault current settings for each zone substation. So at the moment, the min-op fault current setting is 5,000 amps. The reason this min-op fault current setting is needed is because we don't want the bus tie circuit breaker to trip for every single fault that occurs. This is for a number of reasons. Firstly, the asset life of a circuit breaker is dependent on its number of operations. So we want to extend the asset life of the circuit breaker by reducing the number of times this scheme operates, because for faults which have a low fault current, it is not necessary for the bus tie open scheme to operate, so it's not efficient. So that is why we need to define min-op fault current settings for each zone substation. To propose min-op fault current levels, I used two different methods. The first method I used was the 90% consumption method. So with this method, I got data about commercial and industrial customers at a zone substation and their distance from the zone substation. So I worked out the distance at which 90% of these customers were located from the zone sub, and then using a VLOOKUP, I found the fault current for this particular distance. This method is useful because it shows the fault current level at which 90% of the customers will receive the benefits of the bus tie open scheme. The second method I used was a 0.8 per unit voltage sag method. The reason I used this method was based on findings from the University of Wollongong, where they looked at voltage sags at a particular zone substation, and they looked at voltage sags which did and did not cause load interruptions. So as we can see in this diagram, at roughly about 0.8 per unit voltage, we can see that most of the voltage sags that occur do not cause load interruptions. So the method that I used was based on finding the fault current that gave the 0.8 per unit voltage sag, and they are outlined in this table here. So I've got the findings from both different methods, and then using these methods, I proposed min-op fault current levels for each zone substation. A main goal of the project was to model each of the zone substations using the software Siemens PSS SynCal. In this diagram, I have modeled one of the zone substations, and you can see that each of the circuit breakers are represented by element switch times, and you can see the fault on this feeder represented by this fault observation. So the whole purpose of modeling is to analyze the impacts of bus tie open scheme on zone substation assets. So we can see from the PSS SynCal dynamics module the bus voltages with and without the bus tie open scheme. So on the left, we can see the bus voltages without the bus tie open scheme. So we can see that they are constant, so the voltage sag is constant across each bus. On the right, we can see the bus voltages with bus tie open scheme. So in bus 2 and 3, we can see a clear reduction in the voltage sag, whereas there's a deeper voltage sag in bus 1. However, the benefits of the bus tie open scheme are obvious. If we look at the feeder fault currents with and without the bus tie open scheme, we can see that the feeder fault current is greatly reduced with the bus tie open scheme. Now, if we look at the transformer fault currents, we can see that the transformer fault currents is higher in the faulty bus with bus tie open scheme. However, on the other two buses, the fault current has reduced. When the bus tie open scheme operates, the fault current in a transformer increases, and this lasts for a longer period of time due to the inverse time properties of the feeder circuit breaker. This is the major drawback of the bus tie open scheme. In this table, I have used the two values of fault current and time to obtain values for fault energy going into the transformer. So from this table, we can see that the fault energy going into the faulty bus is very high compared to normal operation. However, in the healthy bus, the fault energy is much lower than normal operation. So there are converse benefits of the bus tie open scheme on transformers. On the other hand, we know that the fault current in the feeder and in the faulty bus greatly reduces, and the benefits of this can be seen in circuit breakers. We know that with circuit breakers, the asset life is dependent on the total number of operations and on the fault current that they trip. So if the bus tie open scheme operates and reduces the fault current, this would also reduce the braking duty of the circuit breakers and hence increase their asset life. In this table, we can see the proposed capex value for 2020. And in this column, we have the probability of delay of this capex and then the weighted probability. And then in this column, the potential savings are calculated using this formula. And the formula is multiplication of the capex by the weighted probability by the WACC, which is the weighted average cost of capital, which is an internal value to United Energy, and this is a confidential value, and also multiplied by inflation. So we can see, although that these are percentages, this is a considerable saving of the capex, because this capex value is usually in the range of millions of dollars.
That brings it to the end of my presentation, so thanks for listening. If you have any questions, please feel free to ask me.